Well, good afternoon, everyone, and welcome back to our Bite-Sized Corrosion 2021 Summer School. We've entered our third and final week. We're really delighted to have your company once again, and a very warm welcome to those of you who are new. Bite-Sized Corrosion is a platform for our lunchtime conversations about all things rusty. And this past series has been focused on non-intrusive pipeline surveys, specifically looking at close interval surveys. As we look to today's discussion, we're going to be looking at how we can combine the surveys that we spoke about over the last couple of weeks. Now, you can, of course, catch up virtually on the topics that we did cover. We've spoken about SIPS surveying and DCVG, PCM, and ACVG. Now, you can connect up with those by signing up for free on our Teachable platform, where you'll find those discussions as well as all of the bite-sized corrosion conversations we've held over the last year. Now, having highlighted the various surveys over the last couple of weeks, today we're going to look about the how and why of combining these techniques. And as always, Neil and I will be discussing this together. Neil, I'm going to say, how do you define a combined survey?
As far as I'm concerned, a combined survey really means that you are doing two surveys, or maybe more than two surveys, at the same time. It is a case of being able to measure more than one parameter during a single exercise at the same time, as opposed to what we touched on last week when we spoke about the PCM survey, where people expect to get a combination of the PCM survey and an ACVG to pinpoint the location. Those two surveys are not really combined surveys, they are sequential surveys because they're not done at exactly the same time. You can't do them both at the same time. You have to chop and change between equipment. You've got to do the initial inline current measurements with the PCM, evaluate the situation, go back to the areas of high attenuation, and then locate the positions with the ACVG component of the PCM equipment. So for me, that is not really what I would call a combined survey, but rather a sequential survey.
So do you have an example of a combined survey by your definition?
The combined survey goes back quite some time to one of the very early projects that I was involved in, where we were asked to do some investigation work on a pipeline which had corroded. In order to try and figure out what was happening, I undertook what was then a unique survey at the time, because this was in the early 80s, where we did a combination of a SIPS survey with a Pearson survey, and they were both done at the same time. There's yours faithfully. Many, many years ago, as you can see from the beard and the dark hair. And here I'm wandering through the veld doing the SIPS component of the survey is what you can see in the picture. That's the SIPS equipment. But what we had done was actually taken the output of the Pearson survey, which we saw last week, where you have this typical double spike indication of a defect. And we fed that into the fourth channel of the SIPS equipment, so that both the Pearson and the potential were recorded or logged at the same time at the same place. Now, the interesting thing about this is that the SIPS survey from that particular situation shows us that there were only a couple of very significant defects, which were actually where they had undertaken excavations to investigate the leaks that had occurred on this pipeline. And we had used a temporary cathodic protection system to polarize the pipe. And as you can see from the bottom graph, the pipeline appears to be well protected with no really significant defects. And yet, when you look at the combination with the Pearson survey, you can see that there are in fact some very significant defects, which only hardly even reflect on the potential graph. And the point about this was that the defects were in fact very, very small, and the pipeline polarized very quickly under cathodic protection, but the pipeline had not been cathodically protected. The net result was that where there had been mechanical damage to the tape wrapping, there you can see a fine selected piece of backfill in hard contact with the pipe, causing physical damage to the tape wrapping. And then when you expose one of those defects, this is one of the others, we found that what had actually happened was that at these defects, the water had got in under the pipe, and we had significant bacterial corrosion as a result of the bacterial activity in the water. The combination of the two surveys showed us, firstly, that the defects were there, but secondly, it also showed us that if they had had cathodic protection on the pipe, there would not have been any corrosion.
So just to confirm for me, Neil, when you were combining the techniques, you were wearing those beautiful Pearson ballet shoes at the same time as carrying the SIPS equipment.
Yes, so the what we couldn't actually see in the photograph was that the person behind me, I was wearing one pair of ballet shoes, and the second operator was carrying the Pearson equipment and walking some 5 or 10 meters behind the standard Pearson interval. And the output of that Pearson unit was then fed into the SIPS recording equipment.
Now, I'm not very familiar with the Pearson survey, but the Pearson requires AC as a signal, and the SIPS is obviously picking up the DC. Is there any negative interaction between those signals?
In theory, the challenge with the Pearson always was that it could only survey a relatively short section at a time. And we actually then had to have two signal generators. You had a switched cathodic protection input, and we also injected a Pearson AC signal into the pipe for the purposes of that survey. And at this stage of the industry, the Pearson was very much the go-to survey technique for locating coating defects.
Now, the one I'm most familiar with is SIPS DCVG, and I think it's probably a good idea if we just discuss what that survey technique is in some detail, because it is quite common in the industry.
Sure. Well, of course, the SIPS DCVG combined survey means that we are undertaking both a potential survey and a gradient survey simultaneously. The survey uses the same signal. In other words, it's a DC signal. And the point about the combined survey is that the gradient is in the ground as whenever the DC is flowing. The fact that we use that short pulsed signal in a conventional, what we call analog DCVG, where those of you who've done the survey will be familiar with the term following the flick, where you have an analog meter that flicks. And that is to enable the operator to tell that the signal that he is following is coming from the system that is injected. When you are surveying in combination with the potential, then it's not necessary to have that flick, as long as you can identify whether the differential between the front and back pair of poles is relative to an on potential or an off potential. The difference is then related to the actual potential or the current flow in the ground. So in this graphic, you can see here's the guy with the equipment, and he's tethered to a person about 10 meters behind. And there's a lot of work that's been done, which shows that the 10-meter gradient is probably the most significant to record. And when you look at the graph over here, you can see that whenever there is a defect, there is this characteristic S curve in the gradient signal, which measures the difference between the front and back poles. And what is significant also about this, if you look at the figures, is that the SIP survey is measuring -1 to -1.5 volts, whereas the DCVG survey, the gradient survey, is only measuring a couple of 100 millivolts. So the gradient survey is a lot more sensitive than the actual potential itself. And here is another good indication of the benefit of the static surveyor that we spoke about when we talked about the SIPs. Because the stray current affects both the front and the back poles at the same time, the gradient is not affected by the stray current event. So there's a stray current event. There you can see its effect on the pipeline, and you can see there that there is no effect on the gradient between the two poles because they're only 10 meters apart. The other characteristic that you can see here is that this gradient shape is always a situation where the differential goes positive, it then swings through 0 to negative, with the actual location being where the defect is halfway between the front and the back poles. One of the other benefits of this particular survey is that you can get a good indication of the size of a defect, because you combine the results from the potential measurement, where you are measuring the true on and the true off, as opposed to interpolating between test posts. And you compare that with the strength of the gradient in the soil, and you're able to calculate a relatively accurate area of bare steel. And you can find that derivation in the Bakeman and Schwenk cathodic protection book. And effectively, we then can plot another set of results, which shows defect size as a function of distance. And you're able to actually calculate the defect size based on the combination of the gradient and the actual potential that's measured with the SIP survey.
Right, so that's essentially an additional benefit to the fact that you're saving time and cost by doing the big walk only once.
To give you an example of that, there was a survey we did on a pipeline where the calculated defect size was something like about 0.1 of a square meter. And when we exposed the pipeline, there was a piece of wrapping missing about the size of an A4 page. So it was surprisingly accurate. I'm not saying that every indication will be as accurate, but it certainly is a pretty good indication of what's going on.
Do we lose anything when we combine the techniques? Is there a risk of losing information that we would have obtained if we'd done just the DCVG or just the SIP survey?
I don't think there's any information that is lost in terms of the potential survey, but because you're actually just recording data as you walk, you are not pinpointing the defect at the time of the survey. The defect is only located by interrogation of the data. So again, if we have a look at the situation in the field, and here's a pretty nice picture of a team doing a survey. Front operator with a data logger has a well-defined distance location to within a meter or so, and the person at the back will pass over the same point in the ground 10 meters later. So when you then identify the defect, you have an accuracy of within a meter or two. Whereas if you were using just a straight analog DCVG, where you can move your poles around and precisely locate a point, you can locate that point to within centimeters. But you can't excavate a pipeline 1.5 meters deep to within a centimeter. So from that point of view, it's not really a major problem.
So there's a very practical aspect which results in the information lost or not gained actually is too refined to be of any practical value.
Correct. I mean, the older surveys were based on distance from a known point. So your distance measurement was accurate relative to the field within every single characteristic that you passed, like a fence or a test post or even a big rock. Although it's quite frustrating when you read a report that says that the defect is 5 meters beyond the big rock. This gives you an idea of the accuracy, though. If you have a look at the bottom of the scale, you can see that it is calibrated in about 10-meter distances. And this particular survey shows a whole lot of defects over here, which are very strong indications and very precise indications. And they actually match up with the decreases in potential that were seen in the close interval potential survey. As you can see, there was no stray current in this particular situation, and we didn't lose any polarization during the course of the survey. This particular survey actually was a situation where it was an impressed current system that had been applied over the top of a pipeline that had sacrificial anodes, and every sacrificial anode showed up as a defect.
That must have made for some interesting reading initially.
Yeah,
I think it also highlights, when you find these defects that are very uniformly spaced, you start asking questions. Is that unwrapped joints? Is that a sacrificial anode, or both? When you interpret the data, you need to look at it with your brain engaged.
Absolutely. You need to be familiar with the conditions under which the survey was undertaken. So, for example, if you have a look at this next photograph of some surveying in Central Africa, you should see a photograph of a survey in some pretty dense jungle.
And the pipe was within the jungle?
Both the operators are endeavoring to put the survey poles in the fairly heavy undergrowth. And the challenge here was that because of the encroachment of the jungle, you couldn't actually walk over the top of the pipeline. So what that meant, of course, was that the indications were more diffuse because you're further away from the pipe. And whilst the off potentials are not significantly different if you stray off the pipe, the on potentials certainly are. And it's the on potentials that give us the gradient. So the gradients are more diffuse, which makes a precise location of those gradients more difficult.
Neil, is there a requirement with your combined surveys to survey in any particular direction? Should you be going in a particular direction when you do your survey, or does it not matter?
It's not really a problem. It's more a case of knowing what has happened, so that the guys doing the survey need to be very precise in their record keeping during the survey and not just report back. If you have a look at this photograph now, this particular situation was surveying a number of parallel pipelines. You can see the tracks across the beach there. So that's the one pipeline. The other pipeline was over here. And as you can see, well, you may not be able to see from the photograph, but this is about a 45-degree dune slant. And it's quite a slog to get up the hill when you're carrying the equipment. But what was happening here is that the survey had proceeded from the plant to the beach crossing, and then we had to survey the next door pipeline over the same route. So we moved across, changed the connection to the other pipeline, and surveyed in the reverse direction. Now, if you don't know that that had happened, when you look at the data, you would have seen that the gradient would have been in the wrong direction in terms of the distance calculation. So if you look at the way these people are walking here, the guy with the trailing cable is actually leading, so that the gradient is always measured in the direction of chainage, for argument's sake, instead of just being arbitrary. You may say, well, why is that significant? And the reason for that is this. If you have a look at this graph, remember I said that the gradient has a significant characteristic in that it goes in the one direction first and then the other direction. So that was a defect. Over here, you can see that the gradient is going in the opposite direction. And that is accompanied by an increase in potential of the pipe, which was in between two test stations, and in fact represented a significant stray current interference pickup point as opposed to a discharge point, which helped the pipeline owner to identify what sort of problems he was experiencing.
Interesting. And if you hadn't known the direction that you were recording in, you may not have picked it up.
That's possible.
Quite important that when we take data from the field, when we're gathering the data in the field, we consciously record information accurately. It goes in any survey, but even more so here, so that you don't get upside down and inside out data.
Correct, yes.
Yeah, we've just had a question come in. Do you have any examples of the various combined options that may have enriched the final outcome for the client?
It is a situation where often you find that contract documentation will require certain surveys. And tomorrow we're going to be talking about which surveys are most appropriate for which situations. But there was a situation a few years back where after a whole lot of other surveys had been undertaken, it was necessary to evaluate whether or not the pipeline was acceptable to the end client. The challenge was that the DCVG survey had showed a significant number of defects, and the contractor was then faced with the possibility of having to excavate a large number of defects which had been found and ratified using conventional DCVG technique. And the solution in that case, or the approach, was to then do a combined close interval survey together with the DCVG survey, so that you could tell and evaluate whether or not the defects were significant in terms of cathodic protection. So the point being that with the pipeline under cathodic protection, if the defect was adequately protected by the cathodic protection system, which is what the CP system is there for, then you don't need to repair it. And this particular survey then saved the contractor from having to excavate and repair something like 100-odd defects, which would have cost a pretty packet.
Okay, that's very interesting. Thank you.
I've just got one quick point to make, and that is that having looked at these various combinations, although I indicated that the PCM was perhaps not a combination survey in the sense that I had defined it, it is possible to combine the results of different surveys that are taken at different times, provided you have a common base on which to report the data. And this is where geographical information systems really come to the fore. So if you've got some sort of GIS integration package, you can combine SIPS surveys with PCM results. You can combine pipeline data, be it DCVG or SIPS, with environmental parameters such as resistivity, or perhaps a natural potential survey that was done some time ago, or ground cover. And you may think, well, why on earth would one want to do this? And the reason for that is that there is a technique known as ECDA, External Corrosion Direct Assessment, which is a system that has been developed and formalized by NACE in order to evaluate the corrosion risk on pipelines, which cannot be pegged Pigging being the internal inspection using electromagnetic or ultrasonic tools to determine if there's metal loss. And one of the characteristics of the survey technique is that you do not evaluate a pipeline on any one survey technique or any one set of survey results. You have to look at a combination of a whole bunch of things in order to develop that risk profile. And ECDA is a topic that we'll probably be looking at in a bit more detail next year.
Okay, great. That's really interesting. Yes, I've encountered ECDA as a tool, and it certainly is something that I think many asset owners are looking at as a viable option for surveying and understanding their assets. So I think parking it for next year is an excellent idea. And right now, looking at the time, I think we need to park this conversation. Thanks.